classic encoder-decoder framework for machine translation. And the generation is done by the decoder. So what is called decoding is a generation. So analysis, transfer, decoding is the foundational perspective for machine translation. Now, the pair of languages decides how much of analysis is required on the source side. In particular, if the sentences are very close to each other, then almost word-to-word substitution, or more correctly, morpheme-to-morpheme substitution works and gives you the transmission in the target language. So for such languages, we are not doing any analysis. We are doing word-to-word substitution right at the bottom of the pyramid or the triangle and exiting and entering the target language. This is called direct translation. So this substitution of morphemes was thought to be all that is required in machine translation in 60s, when there was Cold War between US and Russia, and English-Russia and English translation became a very critical task for both countries. Two interesting facts are also this ascending transfer and descending transfer. After analysis, the representation that we get is not sufficient for the generation of the target language, keeping the level same. What I mean by that is that suppose you have created the parse tree for the source language, applying transformation rules on the parse tree, and then generating the target language sentence may not work. We may need more additional information to take it to a higher level of representation, which is closer to interlingua or all disambiguation done. So remember that the T indicates complete disambiguation. The representation has no ambiguity. Okay, entropy of zero entropy representation. So Jyotsna, this needs to be added, that as we go towards the tip of the backward triangle, what we are essentially doing is we are removing all ambiguities. So removing ambiguity completely is not necessary depending on the pair of languages. To give you an example should be there in the slide. मुझे आपको मिठाई खिलानी पड़ेगी. मुझे आपको मिठाई खिलानी पड़ेगी has two senses. मुझे आपको मिठाई खिलानी पड़ेगी और मुझे आपको मिठाई खिलानी पड़ेगी. It is not clear who is giving sweets to whom. So मिठाई खिलाना, खिलाना is the main verb. The agent is not clear. Object is clear. क्या खिलाना हो? And who is the agent? Is it me? Then I'll have to give sweets to you. Or if the agent is up, you, then you have to give sweets to me. So now interlingua based machine translation will require this disambiguation to be done. If you're going from Hindi to Bengali, this disambiguation is not required. Apnake amay mishti khawate hobe. Okay, or translate this into Gujarati. Marathi. This disambiguation is not required. Okay, so this is a good example to show that the pair of languages decides how much of disambiguation is really required. So this is a good example, and Jyotsna, please put it in the slides. It is instructive for students. Now, if the translation is from English to from Hindi to English, then you will have to commit to a particular meaning from the context. Okay, it is not enough to do towards substitution. I have to give sweets to you. that possibly is not the meaning as dictated by the context. Okay, so we have to remember that the higher we go in the Vokwa triangle, more disambiguation we are doing through analysis. Now, another situation is descending transfer. Okay, if you see my book on machine translation, there are examples of ascending and descending transfer. In descending transfer, we again do not remain at the same level of disambiguation, but we come down to a level where the representation can be more ambiguous, can be more noisy or ambiguous, but can still generate a good target language sentence. So this is a point which you are well advised to ponder, keeping in mind the different levels of disambiguation are required for different pairs of languages, and the representation on the target side can be at the same level of disambiguation or lower level or higher level. How do you measure ambiguity? Maybe entropy, perplexity, these are common measures. So this is an important point to keep in mind. Now, framework of by means of parse tree transfer. John eats bread. You create the parse tree, and under the verb phrase, invert verb and noun phrase, and then you get the Hindi order. John bread eats, John roti khata hai. Now, is it possible that you have to ascend a higher level? That means you have to do more disambiguation to come to a representation by which the target language. It's not easy to find out such examples, but ascending transfer and descending transfer work more on the representation than just transforming to the same level of representation in the target language. Okay, so metaphorical sentences, for example, okay, will require ascending and descending transfer. This point also should be on the new slide. Metaphors, okay, may require ascending and descending transfer. Now, the fundamental processes are summarized for machine translation. Analysis is the source language of the source language to represent the source language in more disambiguated form. That's correct. Morphological segmentation, part of speech tagging, chunking, parsing, discourse resolution, pragmatics, etc. are all NLP stages which analyze the source language sentence to give a disambiguated representation as much as possible. Transfer is knowledge transfer from one language. We should more correctly call it representation transfer. And example would be SOV to SVO conversion. Generation is generating the final target sentence. Final output is text. Intermediate representations can include F structure, C structure, tag text, etc. So essentially you do ordering of the words and you do substitution of morphemes. Okay, so and that substitution also can solve the problem of lexical choice. Will you use amma or mummy or mother? Okay, that will be decided by what is called lexical choice. This is also which should be in the additional slide. Now, there are many issues to be resolved, which we saw last time. I went with my friend John to the bank to withdraw some money, but was disappointed to find it closed. So first, disambiguation is part of speech. Bank is noun or verb. Then named entity recognition. John is a proper noun or a name. Then comes words and disambiguation. Bank is financial bank or river bank. Then comes co-reference. Disappointed to find it closed. It refers to what? Bank or money? Bank. And then finally there is this subject drop or ellipsis resolution, where we have to supply the subject for disappointed. Who was disappointed? Okay, so this is known as pro drop or pronoun drop. a very difficult phenomenon in NLP. And the system architecture, of course, for rule-based systems go through different stages of NLP. Many times text simplification is applied to convert a long sentence into short sentences, do translation on the short sentences and stitch them together. So you see, none of the paradigms of machine translation are completely delinked from each other. So this conversion into simple sentences or simple segments is nothing but the phrase table construction, which happens in statistical machine translation. In statistical machine translation, we obtain aligned phrases, and aligned phrases are nothing but the simplified segments of a long sentence. Now, the target generation happens through three fundamental processes. Lexical transfer, that is the morphemes are transformed. Ulga in Marathi, for example, ko becomes la in Marathi, ko becomes ke in Bengali. Morphological synthesis, the word form is changed. Jana becomes jaunga, jaoge, depending on the context. And syntax planning, which is an optimization task. The order of the words are changed so as to convey the syntax of so as to conform to the syntax of the target language. So this gives a good theoretical framework for machine translation, and a practical generation system would have things. The paradigm information for verbs, nouns, that means larka becomes larke, but raja, plural form of raja doesn't become raje, it becomes rajae. So why does larka become larke, but raja becomes rajae, even though both are ending in a? Okay, so this kind of difference exists, and they are called paradigms. Priority matrix decides which word should come in the for example, in the target language sentence. So function word instruction is ko, ke liye, etc. Then case marking happens to get the semantic roles correctly. So that's why machine translation is called an NLP complete problem in some loose sense, because everything in NLP is involved in machine translation. Now we come to statistical machine translation, and you saw this very interesting exercise. If I give you the data of Nesu, Ponese, Nese, Nesau, Yedu, Plavau, and I carry, he will carry, he carries, they carry, I drive, they swim. Then able to do morpheme matching quite easily, and could translate I will carry, they drive, he swims, they will drive. And that was happening because of this clean correspondence between subwords of Czech and tokens of English. So what I mean by that is that I was traced to U, which is a morpheme for Nesu, and carry was traced to Nes, which is the stem for Nesu. So this kind of clean correspondence existed, and therefore it was possible to translate quite easily. That is not to say that Czech English machine translation is easy, not so. Not so. For this small amount of data, it was easy. But it ran into difficulty for Hindi English data, which I emphasize you observe carefully by pick up morpheme correspondences. Okay, so if carry corresponds to dhota, and I corresponds to who, then I carry. Then I will carry can be constructed from dhota and who. Only I'll need some indication of plural in the Hindi language. So if I compare dhota who and dhoega, then it looks like will maps to ega. Okay, then I will carry dhota ega who is not exactly correct. It is not as simple as creating I will carry for check was obtained by obtained as po nesu, because po was the will corresponding to will, the auxiliary verb will. So it becomes little more difficult for Bengali because Bengali has more syncretism than Hindi. The term is called syncretism. Please put it in the additional slide. Syncretism means overloading of morphemes. Okay, so boibe, will carry. This is be is the morpheme for will, but Bengali shows more morphological transformation of words because the morphemes carry more load compared. So it becomes more and more challenging to get these morpheme mappings. So that is where came the statistical machine translation approach. And the foundation was really the argmax computation in the Bayesian framework. So this morpheme mapping, or mapping of text segments on both sides of the parallel data, that is called the alignment problem, and of statistical machine translation. So let's look at the formulation of statistical machine translation, which resembles, by the way, many other problems that worked on transforming sequence to sequence. For example, part-of-speech tagging. If F was the word string and E was the part-of-speech string, then we are interested in that part-of-speech string which has the maximum probability given the word string. And there we applied Bayes' theorem to get the prior probability, which gives me an additional scoring parameter, and probability of F given E, which gives me the probability of the word string given the part-of-speech string. So that gave rise to lexical probability, and PE gave rise to language model probability. Okay, so now for machine translation also, we resort to the same best translation, E tilde. E stands for English, F stands for French. So English, French, the focus of attention for machine translation groups. So I'm referring to the 90s when statistical machine translation was making its appearance slowly, and after some time it would completely overtake rule-based machine translation because parallel data was available and was found to be more effective and more robust than rule-based machine translation. So E is English words, F is French words. English translation, which is obtained by argmax computation on probability of E given F. E belongs to the all possible English sentences. So this argmax will search for the best possible English sentence given the French sentence. And that search would be now converted to probability of French sentence given the English sentence multiplied by probability of E. Probability of E is the language model for English, and probability of F given E is the likelihood of the French sentence given the English sentence. So there was a question about why this turning around of probabilities. What do we gain by converting PE given F, or working with PF given E into PE in preference to PE given F? Is there anything to choose between PE given F and PF? No, not much, but that is also an interesting question. Depends on what is the entropy of the native entropy of the two languages, French and English. So Shannon back in 40s or 50s, I don't recall, computed the entropy of English language through n-gram probabilities. So that exercise has been replicated for other languages also. So an interesting question is, does the relative entropy, okay, between the two languages decide which parameter we would like to work with, PE given F or PF given E? But a more effective consideration is the separation of PE, which is the language model probability. And that gives me a figure of merit for the generated English sentence. So choose that English sentence which has high value of PE. Now, this is an additional parameter which increases my degrees of freedom for scoring. So in classification, of course, there are situations where working with P, F given E is clearly more preferable to PE given F. Okay, we took the example of deciding if a patient has cancer given various data. Now, proceeding forward, the language model is for detecting good English sentences. So the probability of an English sentence W1, W2 up to Wn can be written as probability of W1, W2 up to Wn, which is equal to probability of W1, probability of W2 given W1 into probability of W3 given W1 and W2, and going up to the nth word, probability of Wn given W1, W2 up to Wn minus 1. So this is the application of chain rule of probability. Now, probability of Wn given W1, W2 up to Wn minus 1 is the probability that the word Wn follows word string W1, W2 up to Wn minus 1. So this probability has been so significant in whole of NLP and speech. This probability, predict the next word Wn given the n-1 words preceding it. And sometimes you apply Markov independence assumption and look at a smaller window before Wn. Maybe you look at only the previous word and previous to previous word, which is called the trigram assumption. Okay, this is called the trigram assumption or Markov chain of order 3. So empirically, and no explanation yet for this empirical observation, for English NLP, it seems trigrams are good n-gram probability values or good n-grams which facilitate computation. Empirically, in many tasks, question answering, sentiment analysis, text inferencing, translation, in many NLP applications, it has been found that language modeling for English through trigrams is good enough. So there is a trade-off. If you take longer windows, then you have more information, more context, so better for the disambiguation. But longer windows also means increased data sparsity. There is no guarantee that this long window Wn-1, Wn-2, let's say for 10 words, you will find exactly the same pattern in the training corpus. So it is a trade-off between predictive accuracy and data sparsity. So for English, it seems 3 is a good balance. For Indian languages, we did this exercise long time back, maybe 15 years back. And we suspected that since Indian languages are morphologically stronger than English, most probably 4 would be a good idea, where 4 will operate on morphemes and not words. Okay, it will break the word into its morphemes and take morphemes of length 4. So the 4th morpheme is predicted based on the previous 3 morphemes. So Jyotsna, can you please put this also in the slide? Here the language model for morphologically strong languages depends on language model of morphemes, not really words. And the trigram probability is computed as count of W1, W2, W3 divided by count of W1 and W2. Now, how to get the values of probability of E given F, which is computed through PE and PF given E. Now, E we can obtain by means of trigram probabilities, and which is equal to count of W1, W2, W3 divided by count of W1, W2. How do I get these likelihood probability of F given E? I can do count of f comma e divided by count of e to find pairs e and f of all languages. So to take an example, suppose the English sentence is blue palette, okay, and then the French sentence is mention blue. Blue goes to the goes after mention. Then I have to find out how many times do you have this correspondence blue mention and mention blue, and divide it by number of times blue mention appears on the English side. But this you can see is immediately a non-starter because there is no guarantee that these long sentence correspondences will be found in the training corpus. After all, you'll have to obtain the count from that training corpus. So what do we resort to now? We resort to the idea of smoothing. Instead of working with F and E, we work with parts of F and E. So blue mention blue, you establish a correspondence between mention and blue, mention and mention, and blue and blue. Now, so you need to introduce what is called breaking the sentence into its segments and aligning them. So alignment has played such an important role in machine translation. It has stayed in all paradigms, rule-based, statistical, neural, everywhere alignment has stayed. So alignment essentially means establish correspondence the text elements on both sides of the parallel corpus and grow those elements, those correspondences for bigger text chunks. So for example, if you are doing English-French machine translation, establish correspondence between words and then establish correspondence between phrases. So blue mention, and then blue mention and mention blue. So computing phrase alignment from word alignment is the main task in phrase-based machine translation. So to solve that problem, we have to introduce a hidden variable A that represents the alignments between the individual words in the sentence pairs. So probability of F given E is converted to probability of F comma A given E, where A is a new random variable introduced. And this process, as you know, is called marginalization. Okay, we can introduce any random variable jointly with another random variable. Just make sure the random variable is summed over all possible values of it. Okay, so this is the formulation we have come to. Now, alignment is our which is E1 to L. Notice the notation. 1 is lower suffix, L is upper suffix, lower right suffix, upper right suffix. So E1, E2 up to EL is notated as E1L. So, and the string F equal to F1 to M has M words. So the string French string F has M words. Then the alignment A can be represented by a series A1 to M, okay, of M values, each between 0 and L, such that if the word in position J of the F string is connected to the word in position I of the E string, then AJ equal to I. So you see the alignment is based on how the French words are aligning to English words. That's why J is running from 1 to M, being on the French side. Okay, and I is an integer between 1 to L, indicating Jth French words maps to Ith English word. And if it is not connected to J, so AJ equal to 0 can happen. Okay, for example, boys laugh. English plural nouns don't require a determiner before them, but French requires a determiner always. Okay, even for plural boys, it will have a determiner before this, and that will not map to anything in the English side. And we need not be, thinking about only French and English. We have umpteen number of examples for English Hindi also. So So if you have Ram advised Sham, Ram ne Sham ko salah diya. So ne doesn't map to anything. Diya doesn't map to anything. Or you can say that salah dena, salah diya together maps to advised. Okay, so this formulation is a very nice construction where the index j runs over all the French words and takes a value which indicates the English words position. Now, example of alignment: Ram went to school. Hindi is Ram Pathshala gaya. So Ram went to school. Ram maps to Ram. Went maps to Gaya. To goes to nothing. And school goes to Pathshala. Okay. So if I create a vector for Hindi, then A1 will be 1, A2 will be 4, A3 will be 2, and that's all. Okay, if I run the aligner on the English side, on the Hindi side. Now, from this, we come to a somewhat, daunting probability expression. So we had introduced A as a marginalizing variable, and we had sigma of PRF, A given E for all possible values. Now PRF, E given A itself can be written as probability of M given E, where M is the length of the French sentence and J going from 1 to M. Probability of AJ given A1 to J minus 1, F1 to J minus 1, E, M, E, and probability of FJ given A1 J, F1 J minus 1, M, E. Is an exact expression. There is no approximation here. So probability of the French string and the alignment string given the E string, English string, probability of French string and the aligned string given the English string can be written as probability of M given E. Okay, choose the length of the foreign language string given E. Choose the alignment given E and M. Okay, and choose the identity of the foreign word given E, M, and A. Now, what is happening here? What is happening here is that F, the length of F and length of A are same, 1 to M. Now I can express F, A as F1, A1 as a tuple, F1, A1, F2, A2, F3, A3 up to Fm, Am. Now I apply a chain rule, okay, and have the product of Fi, Fj, Aj, J going from 1 to M. Okay, and M was introduced by way of marginalization. Let's not worry about M right now. We'll see how it came. So you have E already in the conditioning part, and then these AJs are coming because of chain rule. Okay, these AJs in the conditioning part are coming because of chain rule. And probability of Fj, okay, broken as probability of Aj, okay, and then Aj going into the conditioning part for Fj. So if I take probability of A, B, This can be written as probability of A into probability of B given A. So this exactly is happening. So the trick here is to look upon F comma A as sequence of Fj Aj tuple. And those also are broken by conditional probability, probability of Aj into probability of Aj given Fj. Probability of Fj given Aj. So this is what is happening. So I have taken pair Aj Fj, you can see. I have taken probability of Aj and then probability of Fj where Aj is coming to the conditioning part. Okay. And all these F1 to J minus 1, F1 to J minus 1, they came because of the breaking of the joint probability Pfj Aj. I think it will help if I show all the steps, but you can refer to the IBM alignment paper or to standard textbooks on machine translation. Okay, so this looks a bit daunting, but is not so really if you follow the laws of probability. But mathematics being done, there are interesting components in this formula. Okay, in our search for the maximum probability English string, okay, given the French string, the guiding factors are the length of the French string, the alignment probabilities, okay, and the probability of the target language word being conditioned by many different parameters, many different variables. So this gave rise to IBM model 1, 2, 3, 5. Okay, 5 models came from this umbrella expression by using various by making various constraining assumptions. So here is the opening up of the mathematical steps. Probability of F given E is summation over all possible values of A, probability of F comma A given E. This is marginalization. Introduce another parameter M, the length of the sentence. Now, since the target language sentence is changing, F also changes. So I take different values of M. So this is also marginalization. So probability of F comma A comma M given E is sigma M taking all possible values. Probability of M given E into probability of F comma A given M comma E. This is conditional probability. Now summation over M of probability of M given E, probability of F comma A given M comma E is nothing but M summing up J going from 1 to M, probability of Fj Aj pair given A1 J minus 1 F1 J minus 1 M comma E. I apply again conditional probability and see that probability of Aj can be made independent, and then Fj also is made independent, but applying the conditioning that Aj goes to the conditioning part for Fj. So Aj and question of how do I do alignment? Okay, it is ubiquitous in NLP application. Let's say doing automation on movie making or deciphering an unfolding scene, then the alignment is absolutely critical. Suppose you are doing dubbing in the movie. Okay, just now please give this example. Dubbing in the movie, then the frame to text alignment will have to be done. Okay, so alignment is so important. Spell checking, translation, transliteration, speech to text, everywhere it comes as a task. So I illustrate word alignment with a simple example. I have these two sentences. 3 rabbits in English corresponds to Troya Lapa. in French. And the second sentence is rabbits of Grenoble, lapin de Grenoble. So in French, rabbits are called खरगोश, but जिसको हिंदी में खरगोश बोलते हैं, is called lapin in French. Now, this is called a parallel corpus, which is so important for data-driven machine translation. Now you see 3 rabbits, Troya lapin has correspondence at the sentence level. We'll have to uncover alignment at smaller text segments. 3 corresponds to what? Does it correspond to Troya or lapin? And rabbits of Grenoble, what does of correspond to? It corresponds to D, DE, but automation doesn't know it. Okay, an automatic system doesn't know it. Remember that we are not allowed to make any assumption on syntax, semantics, pragmatics, nothing, morphology, nothing. We just have these tokens in sentence alignment. From that, we have to uncover the word level alignments. And that's absolutely fundamental. From word level alignment, we go to phrase level alignment, we go to tree level alignment, but everything begins with word level alignment. Now, I had remarked that in 80s, data-driven machine translation was taught at other places also. Japan, for example, was pushing for analogy-based machine translation. Now, analogy-based machine translation essentially makes use of this. Get these correspondences of smaller text segments and reuse them in a new translation situation. That is called a translation memory. Now, analogy-based machine translation did not have this powerful instrument of probability, or did not really think in that direction, and that therefore, though the concept of translation memory has stayed and always remained very important, it did not give a computational solution to getting translation memory. Translation memory now has become a manual resource, okay, manually created resource, and by all means an extremely important resource. There are tools which keep track of translation memory. Suppose I am a professional translator. So my organization will keep all the translations that I have done in the database. And the segments that I choose for translation, they are valuable indications of phrases which need to be translated. In the last class, you will recall I remarked monotonicity. Okay, that means you rearrange the source language sentence to correspond to the order of the target language sentence and then do translations. So I don't know that rabbits is an animal. I do not know 3 is a number. Okay, all those things are not known. You might say that why don't you do part of speech tagging and then do alignment? You have more signals and more information, more clues for alignment. Yeah, I can do that. But many languages don't have these basic NLP tools. If you take, for example, let's say Swahili language, maybe it will not have. Many Indian languages don't have these basic NLP tools. Why Indian? Most languages in the world do not have basic NLP tools. Okay, so I have only these parallel corpus, and a very celebrated algorithm is for forging the alignment of words. This is called expectation maximization. Let me give you a very quick idea, and we'll dwell on this tomorrow. So EM algorithm starts with the assumption that every word corresponds to every word in the target language. Every word in the source sentence corresponds to every word in the target language. So W, X, Y, Z are on the French side. W is Troya, lapin is X, Y is DE, Grenoble is Z. Grenoble is a place in France, and the machine doesn't know it. And on the English side, you have A, B, C, D. So French word W, which is Troya, can correspond to A, which is 3, with probability 1 by 4, B, C, D with probability 1 by 4. So initially I don't know anything about which word corresponds to which word. So I apply uniform probability. That is the unbiased prior. Okay. So then each soul denotes the transition probability of A going to A going to X, etc. Then I apply maximum likelihood estimate principle. Okay, and from there we get the expected count of how many times WE maps to WF in terms of the translation probabilities or the alignment probabilities. Okay, so this is the expected count. And then from the expected count, I get modified alignment probability. So this expected count computation, which is the expectation step, and alignment probability modification, which is called the maximization step, that goes on alternating, like in EM algorithm. And I show here a few steps. The counts are changed. The expected counts are this now, with initial probability of 1 by 4 assigned to all alignment. Revised probability is obtained. Revised probability is shown here. You see everything was 1 by 4, but now it has become 1 by 2 and 1 by 4. But I'll have to make them probability measures. I'll have to normalize them 1 by 2 and 1 by 4. So that normalization, so this is revised count obtained from the revised probabilities. Probabilities are revised again. Now you see X to B correspondence. This is rabbit, lapa, or lapa. X is lapa. B is rabbit. That correspondence begins to become more and more, suppressing other probability values on the same row. So this goes on happening, and after some time the algorithm converges. EM algorithms necessarily have to converge because EM is a greedy algorithm. And what it maximizes is the probability of the parallel corpus. Okay. And then we get the alignment obtained. Now clearly the EM based alignment is maximizing the likelihood of an expression. What is that expression? That expression is something we'll look at tomorrow, which is in terms of the probability of dictionary mappings raised to the alignment probability per sentence. Okay, so let's discuss this tomorrow. This is a powerful formulation of alignment, somewhat complex, but we'll take a look at it. Okay, so now we can take doubts, questions. But now
there a small doubt. Like at the starting, I missed. There was some breaking of voice, so I wanted to ask. There was one example you told about the sweet. मुझे तुम्हें मिठाई खिलानी थी. So could you just explain that again?
Or repeat that example. Okay. So मुझे आपको मिठाई खिलानी पड़ेगी is an ambiguous sentence because it is not clear who is giving sweets to whom. That part is clear to you, right? मुझे आपको मिठाई खिलानी पड़ेगी.
No, so what is the ambiguity here?
No, the ambiguity is the semantic role ambiguity. Who is the agent? Okay, so the giving of sweets is being performed by me or you. So the English translation for this sentence can be both. I have to give sweets to you or you have to give sweets to me. But when you translate this into Bengali or Marathi, you don't have to do this disambiguation. You can retain the ambiguity and still translate. But not so for translation into Tamil, Telugu, or translation into English. Translation into Assamese, Punjabi, Marathi will work.
Yes, I got it. Thank you.
Hello. Yeah, sir, I had one doubt. Like in the machine translation algorithm, how are we handling the case where there is one to many from one language we have one word and in the translated language we have many. Like for example, if we take from English to Hindi.
लेना,
If we take
सलाह
an
दिया।
example play, then it's खेल रहा है और खेल रही है.
So yes, so this is called fertility, and IBM models don't handle fertility very well. So we move to what is called phrase-based machine translation. So instead of, okay, so instead of establishing alignment between advised and Salah and Dia going to nothing, we establish correspondence between variable length text segments. So we establish correspondence between phrases and not between words, but you have to build phrase alignment from word alignment. Okay.
Okay, sir.
समाज द्वारा दी हुई घर परिवार की जिम्मेदारी औरत अब तक बखूबी निभाती रही है। अब सवाल ये है कि क्या समाज उसको अपने पंख फैलाकर एक नई उड़ान भरने की इजाज़त देगा, जिसका पहला कदम ही शिक्षा है। आइए मिलते हैं एक गांव और उसकी बदलती हुई सोच से।
पहले कौन पढ़ाओ लिखाओ था, खेती क्यारी काम में डांग ढोर में ऐसे करें थे। पहले कौन गौर करे था लड़कियां पढ़ाने की, लड़कियां तो घर से बाहर भी निकाल देते पहले हमारे जमाने में।
कितने साल की उम्र में आपकी शादी हो गई?
मेरी जब तक शादी थोड़ी उम्र में कर दें, 16 साल की थी शादी करी।
तो लड़कियों को पढ़ाओगे अब आप आगे?
ये आजकल के बच्चे तो सब पढ़ाओ हैं। वे हमारे जमाने थे इसे जो खेती करें थे, गाय भैंस रखें थे, ये तो कोई रखता है नहीं, बच्चे उनके माँ बाप वो ना रखें गाय भैंस।
मेरे 4 लड़की है, 2 लड़की की तो शादी कर दी, 2 लड़की के पढ़ाती हूँ। मेरी मन है जो हमारी लड़की जितना पढ़े उतना पढ़ाऊँ, आगे पढ़ाऊँ, आगे बढ़ाऊँ। हमारी लड़की पढ़ने चाहती है, पढ़ने में भी सही है। घर में इतना भी काम ना देती हूँ, मैं पढ़ने के टाइम ज़्यादा देती हूँ, जो पढ़े हमारे बच्चे, पढ़ के आगे बढ़े। और बच्चे तो आगे उनका भविष्य मैं तो खूब पढ़ाने चाहती हूँ। वो लड़की कहती मैं डॉक्टर बनूंगी। बच्चे के ड्रेस मिलते हैं, पैसे भी मिलते हैं। बच्चों को पापा कहते हैं जब पढ़ो बेटा, खूब जितना पढ़ो, मैं पढ़ाऊँ। पापा तो इनका मेहनत करते हैं बच्चे पढ़ाने के लिए।
आपका नाम क्या है?
सोनी।
कितने बच्चे हैं आपके?
3।
कौन, लड़कियां लड़के?
नहीं, 2 लड़की 1 लड़के।
आप पढ़े लिखे हो?
नहीं।
और आपके हस्बैंड?
नहीं, वो तो है 4-5 क्लास पर है।
तो आप बच्चों को पढ़ाना चाहते हो? तो अपनी बेटी बच्चों से मिलाओ हमें जरा।
हाँ, ये लड़की मेरी बड़ी वाली पूजा।
कौन सी कक्षा में पढ़ती है?
12th। ये दूसरा दीपक, ये आरती है।
कौन सी कक्षा में पढ़ती हो?
9th क्लास।
9th क्लास में पढ़ती हो। तो आपको पढ़ाई में कौन हेल्प करता है? मम्मी पापा तो आपके इतने पढ़े लिखे नहीं हैं, तो आप मुझे ये बताओ कि आपको कैसे मदद मिलती है पढ़ाई लिखाई करने में? आपको दिक्कत आती है?
नहीं, स्कूल में टीचर्स पढ़ाती हैं वो, ट्यूशन्स लेती हूँ तो उससे करते हैं।
उससे आप पढ़ाई करती हैं?
हाँ।
अच्छा, क्या बनना चाहते हो?
न्यूज़ रिपोर्टर।
ऊंची आवाज में बोलो।
न्यूज़ रिपोर्टर।
न्यूज़ रिपोर्टर। कि आपको लगता है आपके बच्चे जो बनना चाहते हैं आप उनको उतना बढ़ने देंगी, पढ़ने देंगी?
हाँ, पढ़ने दूंगी।
और शादी वादी का तो नहीं है कुछ सीन अभी?
नहीं, अभी तो मैं सोचा ही नहीं शादी उदी के बारे में।
क्या लगता है कि लड़कियों की किस उम्र में शादी होनी चाहिए?
जब उम्र हो जब भी शादी करना चाहिए, उससे पहले तो पढ़ाई लिखाई जरूरी है।
अब आपको वो उसमें चेंज लग रहा है?